So in this video, what I would like you to do is to calculate this definite integral of the arctangent function, and I'm giving you the answer here. And so if you try it with pen and paper and then come back, I will give you a detailed solution and some comments on it. So see you in a few minutes. Okay, welcome back. Let's look at a solution to this question. So we now want to perform this integral, and initially I don't know off by heart how to integrate the arctangent, but I do know its derivative. So this is a little bit like the integral of the logarithm. When you integrate the logarithm, you say, I don't perhaps know the result for the integral of the logarithm. I mean, you might know it, but when you're first learning it, you don't know. But you do know how to differentiate the log. So therefore, you say, I'm going to write the log as 1 times itself and use integration by parts. And we do exactly the same for the inverse trigonometric functions. So we know how to differentiate the arctangent. It would be 1 over 1 plus, in this case, t squared. So let's use parts and write our integrand as 1 times itself. So let's use the integration by parts formula. It's always good practice to write the formula out. And then we have to make a decision what we are going to integrate and what we're going to differentiate. And that's easy. We're going to differentiate this, otherwise why are we wasting our time with integration by parts? And we are going to integrate the 1. So u is what we call the term that we differentiate. So this is u, and its derivative is 1 over 1 plus t squared. V prime is the term that we're going to integrate. That's the 1, and that integrates to t. So now we have all of the ingredients to put into this formula. So our integral of arctangent from 0 to 1 is going to be u times v, arctan times t. And I'm going to put the t in front because it looks nicer. And I also think if I put the t after the arctan, I'm perhaps more likely to forget it later on. Putting it at the beginning brings it out. So we have t times arctan of t, and that's going to be, because this is a definite integral, evaluated between the upper and lower limits. And then we subtract the integral from 0 to 1 of u prime times v. U prime is 1 over 1 plus t squared, and that's going to be multiplied by t. And if I take this and I multiply it by t, I can just put the t on the top. And that's integrated with respect to t. So now we evaluate this at the upper limit, 1 times the arctan of 1. The arctangent of 1 is the angle whose tangent is 1, and that is pi over 4. That's how the arctangent function is defined. And then we subtract this evaluated at the lower limit, but at the lower limit it will vanish because we have 0 here, and the arctan of 0 is 0 as well. So this vanishes at the lower limit. We now have to subtract, and we look at this integral and we think, oh gosh, this is easy, because this is the derivative here of the denominator. And if you wish, one thing you could do would be you could say, I'm going to put in a factor of 2 here and a half here. So you've multiplied by 1, and then you have got the derivative of the bottom in the numerator. You don't need to do this. You could just leave a space and then work out afterwards what's going on, but you could also do it this way. So now, if we integrate that, we are going to get the logarithm of 1 plus t squared. And we shouldn't forget there's a factor of a half here. Now, if we hadn't written the half and the 2, and you just leave a space, you would say, let's differentiate this logarithm. you're going to get 1 over 1 plus t squared. Excellent. And you are then going to multiply, because we're using the chain rule, by the derivative of 1 plus t squared, and that's 2t. And that would tell us, again, that we need a factor of a half here to obtain t over 1 plus t squared. So on the next line, all we're doing is just tidying this up. This is pi over 4, and then we subtract, and then open brackets, because this minus sign is going to multiply everything in here. And then it's a half, the logarithm, and at the upper limit, 1 plus 1 squared, so the logarithm of 2. And then we subtract, and it's this at the lower limit, so that would be a half the logarithm of 1, because t is 0 at the lower limit, but the logarithm of 1 vanishes, so we'll just write 0 immediately. So that tells us that our integral is equal to pi over 4 minus a half log 2. And we could just say, well, let's pull out a common factor of a quarter. So we have pi here, and then a half is 2 quarters. So we'd have minus 2 multiplied by a quarter times the log of 2. And that's a perfectly good way of writing the answer. But you could also use the rules for logs to write this as the logarithm of 2 squared, or in other words, the logarithm of 4. So that's our answer. Now, I think it's worth, with definite integrals, if we can, thinking, does the sign work? It's very rare that you can say the exact number is correct, but if I look at this, I can see that it's positive. Pi is a number a little bit bigger than 3. And so pi is a bit bigger than 3. And 4 is a number that is somewhere between e, which is 2.7, etc. So it's bigger than e. So the log of a number bigger than e means it's bigger than 1. But 4 is certainly less than e squared. So the log of 4 is certainly less than 2. So this logarithm is somewhere between 1 and 2. So we've got a number a bit bigger than 3, and we're subtracting from it a number which is between 1 and 2. So this is positive. And we expect it to be positive if we look at the integrand. The integrand ranges between 0, arctangent of 0, and pi over 4, arctangent of 1. So it's going to be increasing this function, and it's ranging between 0 and pi over 4. So it's positive as expected. And that's always worth thinking about with a definite integral if you can. Okay, on the next slide, I'm going to give you an exercise to look at. So the method that we used on the previous slide can be extended to looking at the integral of the arc sine, and I am just giving you here a very similar exercise for you to carry out, and this is the answer. And with that, I'll stop this video.